Hello everyone, I'm Qiang from Qingdao University. First of all, thank you for listening to my speech. The title of my speech is a random reversible watermarking solution for relational data. Let's start without seeing more. Relational databases are widely used and shared due to the increasing use of the internet and cloud computing. However, the remarkable increase in the creating, transfer and sharing of the database comes with security risks, such as data theft, illegal copying, and copyright violation. So how to protect data security and prove data ownership in an open and shared environment has become one urgent issue. Database watermarking is a recently proposed technique for database copyright protection. Before distributing the data owners embed their unique copyright mark into the data with a watermark embedding algorithm, and then distribute the data through public channels. Then the data owner extract a unique copyright mark from the stolen data for copyright proofing. To protect data copyright more effectively, the watermark embedded in the data must have the following properties: robustness, impersonability, embedding capacity. The robustness of the solution is the ability of data owner to extract watermarked information from the data, even if watermark has been compromised. Impersonability usually means that the watermark information does not cause obvious distortion to the data. The embedding capacity refers to the number of bits of watermark that can be embedded in a given amount of data. These three properties influence and constrain each other. For example, the fewer number of watermark bits embedded in the data, the greater the impersonability of the watermark. Relational related work based on digital watermarking solutions for mutual media data. Researchers have proposed several watermarking solutions for relational data. In 2002, the best known solution was proposed by Reversible and Qiang. They assume that users can tolerate a certain degree of data distortion, some special value, which constitute a digital watermark, are embedded into special bit of some of the attribute value of some tuples. The selection of embedding position is determined by a secret key. In 2006, John ETL proposed the first reversible relational database watermarking solution, called HSW. After then, a number of watermarking solutions have been proposed, such as DW, PW, RW, and JW, which are not listed here. However, there are still problems with database watermarking technology. The most traditional reverse watermarking solutions are based on carry modifications and have to balance watermark robustness and data distortion. It seems that robustness of watermarking and data availability can't be achieved at the same time. To solve this problem, we propose a random watermarking solution for relational data, which improves the robustness of watermarking while reducing data distortion. Its experimental results show that our solution is better than the previous solution in terms of robustness and data availability. The solution main includes the following five main phases. Processing, watermark embedding, watermark integrated detection, watermark extraction, data recovery. These five phases are described in detail below. The first step of processing is encoding the data owner's copyright information into a watermark sequence that can be embedded into the database. The second step is selecting the attribute suitable for embedding the watermark. The final step is to generate a random function to determine the proportion of each tuple in which the watermark will be embedded. The main task of the watermarking embedding phase is to embed watermarking into the database in an invisible way, determining the table's attribute and the position bit, and then embedding the bit. After embedding the watermark, the data winner stores the auxiliary data MP and uses them during the watermark integrity check, watermarking extraction, and data recovery phase. Here we take one as an example. Then to determine the position of R, the prime key of the tuple and the KP are hashed. Then 3 determines whether the tuple is watermarked or not, and 1 eta controls the tuple embedding radio. Then 4 determines for each attribute whether the attribute is embedded into a watermark bit or not. Then 5 and 6 generate a random number and attribute in the tuple with a radio of 1 omega will be watermarked. The value of omega is determined by the key, the prime key of the tuple, and mass. This approach increases the watermarking capacity and the randomness of the watermark embedding. We can adjust the data distortion by adjusting the mass. Then 7 selects 1 bit from the watermark string and the embedded bit, mu being the length of the watermark. Then 8 selects the bit position for embedding. C is the number of the least significant bits. Then 9 combines the watermarked bit with the original information using an exception or operation to generate a new bit. Then 10 connects the embedded watermarked bit with the subscript of the watermarked where it's located to create the auxiliary data beta SL with the embedded watermarker and watermark position information via equation. Then store MPI and beta SL means to store the beta SL into the auxiliary array element MPI. MPI represents the auxiliary data for position I. Update beta key bitas. In lane 12, update the case bit of the latest significant bit to bitas. Finally, the auxiliary retains the embedded watermarked data DW and the auxiliary data MP. To ensure that the data winner can detect its watermark in case of several attacks, we check watermark integrity of all positions. The algorithm only detects all tuples when the data does not contain watermark information. When all positions have a marker array of 0, the data does not contain corporate information. The watermark extraction algorithm is shown in algorithm 3. When the quality of data is not sufficient to meet the demand, the data will be useless. The data winner listens the key and supporting fields to the data user, who then uses the key and data recovery algorithm to recover the original data. The data recovery algorithm is shown in algorithm 4. This section evaluates various aspects of the solution. The experiment aims to verify the accuracy and robustness of the solution. The experiments include satisfactory distortion experiments, watermark capacity experiments, and robustness experiments. Watermarking inevitably kills the distortion of the data, and the longer the watermark, the more severe the distortion. There are Therefore, we compare some satisfactory metrics of the origin and the watermark database. The result of the comparison was compared with other solutions such as DW, JDW, PEW, and JHW. To visualize the effect of watermarking on data distortion, we calculate the mean standard deviation and mean absolute error before and after watermark embedded data, and the value of MAU is calculated from above equation. The table shows the experimental results for each attribute of the database, and the results are compared with other solutions in the table. To realize the change in mean and variance and difference in mean, DM and difference in standard deviation, DS, for each attribute are given in table. DM and DS are calculated by left equation, where MED and STD represent the original database mean and standard deviation values. Mean DW and STD-DW represent the mean and standard deviation of the watermarked database. The table shows the experimental results for each attribute of database compared with the others in the table. Watermark capacity is a measure of ability of the watermark to resist attacks. The more bits of information the watermark has in certain moment of data, the more resistant the watermark will be against the malicious attack. The left figure shows the change in watermark capacity under different number of tuple and 1 eta in Qiang 1.5. The right figure shows the difference in the number of embedded watermark bits and by varying the value of 1 eta when the number of table is 100,000. Number of bits embedded in the data is similar to the mathematical inference. The experimental results are consistent with the inference results within the error tolerance. In this section, different attacks are performed on the watermarked data. These attacks include tuple addition attacks, tuple modification attacks, and tuple deletion attacks. We also compared with other solutions such as DW, JDW, PW, and RW. Tuple attack addition attack is in this type of attack. The attackers may insert several randomly generated tuples into the watermarked data. As shown in left figure, when the same amount increases the number of tuples as the original data, the detection accuracy of our solution remains 100%. At this point, the detection accuracy of DW is already less than 88%, and the accuracy of PW is only 98%, as shown in right figure. After inserting 100% of the tuples, 100% of the watermarked data can be gathered accurately. For elevation attack in this type of attack, the attacker changes some tuples as random. Here we perform a bit inversion attack on all attributes of randomly selected tuple to interface with the watermark detection. As shown in left figure, when 90% of the tuples are alerted, our solution still maintains 100% accuracy in watermark detection. Tuple deletion test in this attack. Attacker removes a certain number of tuples at random, trying to interface with watermark detection by removing tuples containing watermark information. Watermark detection shown in left figure. When 19% of the tuples are deleted, our solution can still maintain 100% watermark detection accuracy. When many tuples are deleted, the detection accuracy of JDW, PW, JD, HSW, and other methods except RW decreases significantly. The data recovery is shown in the right figure. Aiming at the problem that the watermark information extracted under several attacks is incomplete. A random reversible watermarking solution based on ISB modification is proposed. Watermark embedding algorithm, watermarking integrity checking algorithm, watermarking detection algorithm, and data recovery algorithm is designed. The watermark capacity is improved by embedding mutual watermarks in the selected tuples. The randomness of watermark information distributed is increased by controlling different tuples to embed a unique proportion of watermarkers. When extracting the watermark, the accuracy of watermark detection is improved by discarding the attack bits. Finally, the supreme satisfaction distortion watermark capacity and robustness improvements are nearly analyzed. Thus, we can draw some conclusions. Firstly, our solution can resist several types of attacks. Secondly, the impact of embedded watermarks on data availability is small compared with DW, JDW, RW, PW, and JSW. Our solution has better attack resistance and causes less data distortion, which can meet the requirements of most application scanners. That's all. Thank you.
Hi, this is Niusen. I'm a PhD student from Michigan Technological University. The topic of my presentation is enabling accurate data recovery for mobile devices against malware attacks. This is a joint work with Wenxie and Dr. Chen from Michigan Tech. Mainstream mobile computing devices have been suffering from various malware attacks. The malware may compromise the OS and further corrupt the data. It is difficult to combat this type of malware due to its high system privilege. Therefore, it is important to guarantee that the valuable data can be restored to the exact state right before the malware compromised the devices. Here, we give a definition. We define the time right before malware corruption as the corruption point. Currently, there are two approaches to achieve data recovery. The first one purely relies on a remote version control system. However, this scheme cannot achieve data recovery guarantee since the OS level malware may compromise the most recent data changes in the device, which have not been committed remotely, and the remote server can only allow restoring the historical state of the data rather than the exact state at the corruption point. The second approach purely relies on the local storage. This scheme will maintain a local version control system. However, due to the limited local storage capacity, the versioning data can only be returned for a short term. Some works also incorporate malware detection in local storage to avoid retaining too much unnecessary historical data. But the malware detection may suffer from false negatives. Therefore, the data corrupted by the undetected malware may be lost. In this work, we aim to ensure the recovery of the data at the corruption point after the mobile devices suffer from malware attacks. Before I introduce our design, I will first introduce some background. Flash memory is widely used as the storage for mobile devices today. Flash memory has some special features. Flash memory consists of many blocks. Each block consists of many pages. The first feature of flash memory is the unit of read and write operation is a page, but the unit of erase operation is a block. The second feature of flash memory is erase before write, which means if you want to write some data to a page, you have to erase the whole block first. Third, flash memory has a limited number of program and erase cycles. We call it PE cycles. Due to those special features, update operation in flash devices is not friendly, since overwriting a page requires first erasing the entire block. But write is performed in pages, while erase is performed in blocks. Therefore, in-place update strategy in flash memory will bring a significant overhead. Instead, flash memory prefers out-of-place update. Flash translation layer is often used to manage raw flash memory so that flash storage can expose a block access interface to be compatible with traditional block-based file systems. Products like SD card and eMMC use FTL to manage flash memory. FTL provides some special functions like address translation, garbage collection, well leveling, and bad block management. The next part is ARM Trust Zone. ARM CPU are the leading mobile processor on the market today. ARM Trust Zone technology offers an efficient, system-wide approach to security with hardware-enforced isolation built into the CPU. It creates two execution environments, a non-secure world and a secure world. The secure execution environment, which can be used to run sensitive applications, and a non-secure execution environment, which can be used to run non-sensitive applications. Each world operates independently when using the same processor, and switching between them is orthogonal to all other capabilities of the processor. Also, secure world is isolated from normal OS. Therefore, the OS level malware cannot compromise the secure world. The next part is our models. The first one is our system model. Our system model mainly consists of two components, a mobile computing device and a remote cloud server. The mobile device is equipped with a flash-based block device as external storage and ARM processors with trust zone enabled. The flash memory is transparently managed by the FTL, exposing a block access interface. The cloud server runs a version control system and interacts with the mobile device. The next part is our attack model. We mainly consider an attacker which performs data corruption attacks. We consider the strong OS level malware which can compromise the regular operating system running in the trust zone normal world and corrupt any data visible to the operating system. Trust zone is secure, and the malware cannot compromise the secure world, including the trusted applications and the data in it. The malware is not able to hack into the FTL. The communication channel between the mobile device and the cloud server is assumed to be protected by TLS or SSL. The malware will not perform arbitrary behaviors like blocking user IOs or conducting DOS attacks, which could be easily noticed by the device owner. Next, we will move to the design of MobiDR. Our design will also rely on a remote server. The data stored in a computing device are periodically backed up to it. The most challenging part is how can we guarantee the recovery of data to the corruption point? Let me use this picture as an example. For instance, at backup 1, we commit the data to a remote server. Then the user performs some write and read operations. Next, at the corruption point, which is T0 in this picture, the device is compromised by the malware. The malware performs a read and write operation. At backup 2, we back up the data to the server again. Suppose then the malware is detected and the device owner wants to recover his or her own data. For now, the device owner has only two choices. The first choice is to restore the data to backup 1, but this will miss the few new data which are written after backup 1. The second choice is to restore to backup 2, but this will contain the corrupted data which is performed by attacker. The user's goal is to restore to T0. Our key idea to resolve this problem can be described as follows. As you can see in this picture, this is the most recent backup point. After that, the user writes new data A and B to the device. Meanwhile, in the flash translation layer, the data A and the data B is stored in flash page 1 and flash page 2, respectively. Then the device is corrupted at T0. For instance, we assume the malware is ransomware. It encrypts data A, and the encrypted data A prime was written to page 3, but the original data A was still preserved in flash device for some time due to the out-of-place update. Also, the attacker encrypts data B, and the encrypted data B prime was written to page 4. The original data B was still preserved in page 2. Therefore, by leveraging this special nature in flash memory, we can recover the data to the corruption point T0 with the most recent backup plus A and B. This is the core idea of our design. Our design can be summarized as follows. We build a virtual version control system across the cloud server and the mobile device. Periodically, we securely commit changes of data in the local device to the server. After a malware attack, we will retrieve the versioning data from server, extract the most recent data from raw flash memory, and combine them to restore the data at the corruption point. Our design includes 4 components: version control server, dRecover, drback, and drftl. Version control server runs a version control system. dRecover conducts data recovery. It runs in a normal world. drback will periodically conduct data backup. It contains an untrusted application which runs in the normal world, and a trusted application runs in the secure world. drftl is a specially designed flash translation layer which transparently manages the raw flash and works with the user-level app for data backup and recovery. For the details, drftl will keep track of the delta data while maintaining a stack in the internal RAM. It will collaborate with drback to periodically commit the data in the stack to the flash, and collaborate with dRecover to restore the data to the corruption point. For DR-back, it works with DRFTL to extract the most recent Delta data and send them to the cloud server after having verified their correctness. The backup process is also run in DR-back. To enter the backup mode, we will issue a secret read sequence to the reserved LBAs, and 2 read operations are performed. The first read will return the data of the page, while the second read will return the current version number, the page sequence number, and the tag. After all new Delta data are read, DR-back will inform TA to verify the Delta data and commit them to cloud server. For the D-recover, it will collaborate with the DRFTL to restore the data to the corruption point. The restore process will retrieve the most recent data from flash memory and retrieve the most recent data from cloud server, check the integrity, and place them to the flash. There are 2 cases need to be handled when localizing the corruption point. Please check our papers for details. We then implement MobiDR in real-world devices. DRFTL is ported to LPC H3131. D-recover was run in Firefly, and the DR-back was run in Firefly and Raspberry Pi. We first evaluated the backup phase. The backup process is conducted by DR-back together with DRFTL and the remote version control server. The DR-back needs to first extract data from the raw flash memory to the user space by working with the DRFTL. This sub-process is taken care by the CA of DR-back, which runs in the normal world. The DRFTL computes text for the data being extracted. The results are shown in this figure. We can see that the throughput for data extraction is about 1 megabytes per second, which is regular for a USB 2.0 interface. The throughput for computing the text in RPC H3131 is around 100 kilobytes per second. This is reasonable for a low-power electronic board. After having extracting the data, the DR-back will verify integrity of the data based on the associated tags and send them to the remote server if the verification is successful. This sub-process is taken care by the TA. The throughput for these TA operations is about 250 kilobytes per second. The major computation in the TA is to verify the correctness of the tag, which requires a similar computing workload compared to the tag generation. The performance of the tag verification in Raspberry Pi is 2 to 3 times better than the tag generation in LPC H3131, which makes sense since the Raspberry Pi is more powerful than LPC H3131. We then evaluate the recovery phase. We first evaluate the throughput of retrieving the most recent data version from the server and committing it back to the flash. The experimental results are shown in this figure. The throughput for data retrieval is around 50 megabytes per second, which is reasonable since the communication happens in a local area network. The throughput for data verification is around 9 megabytes per second. This is because Firefly is a high-end electronic board with performance comparable to the desktop. The throughput for data commit is around 2.5 megabytes per second. This is reasonable for a USB 2.0 interface. Compared to the data extraction, the throughput for data commit is 2 times faster. This is because the data extraction requires additional read operations for obtaining the text. We also evaluate the time needed to localize the closest data version to the corruption point. Because the corruption point may occur before the most recent backup point. Therefore, we will use a binary search to localize the closest data version. We create 64 data versions, and the delta size is 2 megabytes. After the DLFTL has retrieved the most recent data version, it will localize the closest data version following a binary search manner. The results show that when the version number is 32, it has the minimum search time since it is the middle point. At last, we evaluate whether MobiDR can recover a given file accurately by placing the raw data back to the flash memory. We tested 100 files with different types, and the recovery rate is 100%. In this work, we have designed MobiDR, the first secure data recovery system which can allow a victim mobile device to restore its data at the corruption point when suffering from malware attacks. Experimental evaluation confirms that MobiDR can ensure recoverability of data at the corruption point at the cost of a modest extra overhead. This is all my presentation. Thank you.
Hello everyone, and welcome to the presentation on bootstrapping trust in community repository projects. Community repositories provide an easy and efficient way for software distribution. They are very popular in the open source communities, and over the last few years, their popularity has only increased tremendously. For example, PyPI, which is used for distribution of Python packages, sees about 400 million downloads per day. RubyGems has seen about 83 billion downloads since its creation. And NPM, which is used for distribution of Node.js packages, sees about 500,000 downloads per day. But since the popularity has increased, so has the number of attacks. There have been numerous instances where the end users have been fooled into downloading unauthenticated packages. We will now look at some of these recent attacks. A software project hosted on PyPI repository was downloaded thousands of times before it was detected that it contained malicious code that corrupted the user's machine, and the package was finally removed from the index. A fake Roblox API package was hosted on the NPM repository. When the user downloaded and installed this package on the machine, it also installed a ransomware that corrupted the user's system. A package hosted on PyPI was detected to contain malware, and the package was downloaded by many users before it was detected and removed from the index. A similar attack was also detected on packages hosted using the RubyGems repository. So, now the question that we have is that how can an end user obtain an authentic version of the software package as was intended by the project owner? A simple solution here is that the project owner can sign the package, but then in this case, we again have to deal with the distribution of the public key required to verify the signature. So now our question translates to, how can an end user obtain authentic version of the project owner's public key? Can any of the existing mechanisms help? In order to answer this question, we will look at some of the popular package signature mechanisms used by developers. The first mechanism that we will look at is the code signing mechanism. A code signing certificate binds the publisher's identity to a public key. Thus, a code signing certificate provides validation of the publisher, assures the software integrity, and establishes trust in the publisher. But the code signing certificate process is cumbersome and complex. As a result, this approach has its own drawbacks. The process of obtaining a code signing certificate requires manual verification of the publisher's identity. This requires the certification authority to make human intervention for the process. As a result, the process cannot be automated, and because this is economically costly, it is more popular among businesses and is mostly endorsed by large publishers like Microsoft, Apple, Adobe, etc., and is not very ideal for open source packages or for individual or freelance developers. And as a result, this approach sees low adoption rates among the developers. The second mechanism that we will look at is the package signatures. There are two different types of package signatures used by developers. The first one is signed by repository. Repositories like NPM sign all the packages that are uploaded using a repository key, and the corresponding public key is then publicized and can be used to verify this signature. Since all the packages are signed using the same repository key, if the repository key is compromised, it leads to compromise of all the packages in the repository. This approach doesn't guarantee the ownership of a package by the publisher and is more focused towards proving the integrity of the software. The second type of package signatures are signed by author type of signatures. Some repositories like PyPI and RubyGems allow the publishers to generate GPG signatures for the packages that they upload. The corresponding public key is publicized using out-of-band methods. But again, as we do not have a mechanism to verify the authenticity of the public key, this approach sees low adoption rate. Again, this approach does not guarantee the ownership of the package by the user. So both the mechanisms that we saw in the slides are more focused towards proving the integrity of the software or establishing trust in the publisher, but not on proving the ownership of the project by the software publisher. The approach that we propose here is more focused on proving ownership of the project by the software publisher rather than proving integrity or establishing trust in the publisher. The approach that we propose here is a mechanism to certify validity of the software projects that are hosted on community repositories. This approach leverages existing PKI model and is inspired by highly successful ECMI protocol used for X.509 certification of domain names. In this approach, the publisher provides proof of ownership of the project in order to obtain the certificate. The approach is fully automated on the server side, and the deployment of this approach does not require any changes to the community repository, so it can be deployed right away. We will now look at the software certification service. This service is a certificate authority that issues free certificates for software projects. A project certificate binds the project owner and the project name to a public key. In order to obtain the project certificate, the project owner needs to engage in a protocol with the server in order to prove ownership of the project. As pointed out earlier, the proposed approach is based on the ECMI protocol, so we will now have a look at how the ECMI protocol works. When a client wants to request a certificate for a domain name, the client will place the request to the server. In response, the server will send a token that the client will need to provision at a specified location in order to prove the ownership of the domain. Once the token has been received, the client will place the token and complete the challenge and notify the server that the challenge is being completed. On receiving the notification, the server will go ahead and check for the presence of the token and also check for the validity of the token. Once the validation is successful, the server informs the client that validation is completed and then issues the certificate for the domain name in question. We now look at the threat model that has been considered for this work. We assume that the SCS private key that is used for signing project certificates is not compromised. We also assume that all the communication between the SCS server and the client happens over a secure channel. We consider three different types of attackers for this threat model. We consider attackers that gain access to the client's SCS account. We also consider attackers that gain access to the repository account, or in other words, the project repository hosted using services like PipePI or NPM. We also consider attackers that are capable of executing a man-in-the-middle attack between the SCS client and the server. We now look at the security goals for this certification protocol. The protocol ensures that only an entity that controls an identifier should be able to successfully complete the certification for that identifier. The protocol also ensures that messages generated during one execution of the protocol for one account cannot be used towards obtaining authorizations for other accounts. The protocol ensures that attackers that are able to gain control over a project's repository for a short period of time are not able to successfully complete the certification protocol. Lastly, the protocol ensures that anybody who can access project's website is able to know whether an instance of a certification protocol is running for that project. We now look at the overall system for the SCS protocol. This system consists of 5 different phases. In the first phase, the client will request for a project certificate and prove ownership of the project. In the second phase, in response to the request, the server will issue the project certificate. In the third phase, the software publisher will sign the software project using the private key of the corresponding to the certificate public key, and the signed package is then uploaded to the community repository. And in the last phase, the end user downloads the package, checks for the validity of the signature and the certificate, and then installs the software for the further use. The SCS protocol that we propose here consists of 2 major phases. The first one is registering an account with the server, and the second one is requesting the project certificate. The first phase is executed only once when initially the client starts to communicate with the SCS server. But the second phase is repeated every time the client has to request a certificate for the project. The second phase consists of multiple steps like placing an order for the certificate, completing the challenge to prove ownership of the project, and finalizing the order by placing the certificate signing request and downloading the certificate that is issued by the server. Now we look at the different key pairs that are used by the SCS protocol. This protocol uses 3 different types of key pairs. The first one is account authentication keys. This is a public-private key pair which is used by the client to sign the messages that are sent to the SCS server while executing the protocol. The second are certificate keys, which is again a public-private key pair. The private key in this key pair is used for signing the project, and the corresponding public key is used to verify the signature. The third one is the repository key. These are the credentials that are used by the project owner for logging into the project websites. We now look at the first phase of the protocol, which is account creation and registration. For this phase, the client will generate account authentication key pair and a registration request containing contact details, public key, and the signature using the private key. On receiving the registration request, the server responds with a new order URL, where the client can later on place the request for the certificate. Coming to the second phase of the protocol, the client will generate an order for the certificate, and the order contains details like the identifier for which the certificate is requested. In our case, it's the software project name, type of identifier, which in our case is package or project, not valid before date, and the not valid after date. On receiving the new order request, the server responds with a challenge URL where the client can complete the challenge to prove ownership, and the finalized URL where the client can place the certificate signing request. On receiving the challenge URL, the client completes the challenge to prove ownership of the identifier. Once the client completes the challenge, the client generates the certificate signing request having following information. It has the identifier, it has the public key, it has the owner details, valid from date, and the expiration date. And using this signing request, the server generates the project certificate, which can be downloaded by the client. Now we look at the steps for proving control over the identifier. The identifier authorization establishes 3 different things. It establishes that the client controls the private key of the account authentication key pair. It establishes that the client controls the identifier in question, and that the client controls the private key of the certificate key pair. But proving that a client controls the identifier is a hard problem. In our case, in order to prove ownership of the project owner provisions some information on the project's homepage. The SCS server generates a token, which is a random string, and sends it to the client. On receiving this token, the client displays the token in the project description section of the project page and notifies the server that the challenge has been completed. On receiving the notification, the server checks that the token exists in the project description portion of the web page and also checks for the validity of that token. The image here shows the token displayed on the RubyGems homepage and on the PyPI homepage. The question now we have is that what will happen if an attacker gains the repository access? Here, in this case, we are mostly concerned with attackers that gain access for a shorter period of time, because if an attacker gains access to the repository for a longer period of time and can make changes to the project homepage, we make sure that the token that is displayed to fulfill the challenge is displayed visibly, so it is easy to detect, either by the project owner or by the end user who visits the project's homepage. But we are concerned with the attackers that gain access for a short period of time, making it difficult for the owner to detect the attack. In order to stop these types of attackers, we make sure that the client displays a new token periodically for a longer interval of time on the project homepage. For example, the client can display a new token every day for 7 days in a row. So the attacker will need to control the repository for 7 days in a row in order to get certificate for the project. This period is called the identifier verification window. Now, what will happen if an attacker is able to display the token challenge every day and remove it after the check is done? In order to stop this, once the server has been notified about the challenge completion, the client will need to maintain the token for a certain amount of time. This period is called the challenge verification window. The server will check for the token multiple times at random moments in time during this window. We now look at the compromise resiliency provided by the protocol. Since the protocol makes use of different types of key pairs, the compromise resiliency also depends on what key pair has been compromised. If a repository key is compromised, it leads to compromise of the project repository, which also includes the project description section where the challenge token is displayed. In these types of attacks, an attacker may attempt to get a certificate or can tamper with the response token that is displayed on the project homepage. Even though the protocol cannot completely avoid this type of attack, this attack is possible to be detected because either the project owner or the end user will be able to see the token challenge displayed or changed in case of the attack and will be able to detect the attack. In case of the account authentication key pair being compromised, the attacker will attempt to get a new certificate for the project in question, but the attacker will not be able to complete the identifier authorization because the attacker does not control the repository key that is required to complete the challenge. Deployment to community repositories. The deployment of this protocol does not require any change to the community repositories, so it can be deployed right away. At present, we have deployment for PyPI, NPM, RubyGems, and GitHub repositories. Summarizing the work, the attacks on community repositories have increased in recent past. As a result, a mechanism to ensure integrity and authenticity of packages hosted using these repositories is required. In this work, we designed a certification service for community repository that issues a certificate for the package. The protocol requires the publisher to prove ownership of the package. The protocol is fully automated on the server side, provides compromise resiliency, and can be deployed without any changes to the community repository side. This completes the presentation. Thank you for patiently listening and following along.